we go on with the last speaker of today, Vicente Grau from the University of Oxford, and he will talk about data analytics and computer simulations for the study of cardiac diseases. Vicente, please go ahead.
Yes, can you hear me?
Just perfect.
Perfect, great. Yeah, we are changing topic a little bit here. We are going to talk about whole organ simulations, and I'm going to talk in particular about the things that we've done up to now, mostly separately between the computer simulations work that we have been doing and the work on data analytics using machine learning, and how we are expecting for these two lines to converge during the CombioMed 2 project. Okay. Let me just go back to my presentation. Yes, that must be it. Okay, perfect. So here is a purely computer simulation work that we have been working on. We are establishing a pipeline between cardiac images of a specific subject. In this case, is cardiac magnetic resonance, and on the right, the simulations, in this case, electrophysiological simulations of the electrical activity of that particular patient from the heart all the way to the electrocardiogram ECG signals that can be recorded on the torso. So the idea is that we have a pipeline that goes from this specific personal CMR slices of that patient or that subject to their electrocardiogram as simulated. Obviously, there are a number of parameters that we have to set in that pipeline that are not available from the images, and there is a considerable natural variability of those parameters and also pathophysiological variability when we introduce disease. And in order to be able to fine-tune the model or calculate the optimal parameters, then we have to do perform a large number of simulations. The pipeline that we have implemented is heavily based on machine learning tools, particularly deep learning. We have to take the clinical MRI slices, we have to segment them. And this is all done using deep learning models. So we segment the surfaces of the left and right ventricles. We also segment the surface of the torso. We segment lungs and ribs, which can also affect the conduction of the signal from the heart to the electrocardiogram electrodes that are placed on the skin. We use population models to fit a model of the torso, since we don't have enough information for those in the images. And finally, we produce meshes with these, and we then perform high-performance computing simulations by which we can estimate or simulate the electrocardiogram on the surface electrodes, and we can actually compare these with the signals measured from that same patient, so that we can look for differences and then try to match this difference with possible either pathology or just different values within the natural variability of a number of parameters. We have started to use this in practical applications. This is a paper that we published recently, in which we were trying to use this pipeline to analyze what is the effect of different heart orientation and different anatomy of the torso of a patient on the signal that is measured in the electrocardiogram. So here we can see it's the same heart geometry that we took from one of the subjects, and we placed it at a number of different locations in the torso, and also used a number of different torsos which also come from different patients. So one of these is the actual patient from which this heart geometry comes, and the others are other subjects from the same group. And we analyzed in this way, using a small number of simulations. We are able to get some conclusions about what happens with differences in torso volume. This doesn't seem to affect the QRS amplitude, at least, and what happens with heart orientation. So we can get a certain link between the orientation of the heart and the morphology of the ECG signals from different electrodes. Now we can only do this at this point by using a small number of simulations, since these simulations require a substantial computational infrastructure. So at this point, we have only done a handful of simulations to get some kind of qualitative understanding of the link between this location and torso volume and the electrocardiogram. And we would like to be able to do this in a systematic way by doing thousands of or millions of these simulations and then getting a proper explanation of these links. Here are some of these conclusions that we have reached. What happens when the heart geometry rotates around the long axis, the left to right axis, what happens when it moves in the lateral direction, what happens when it moves along the craniocaudal direction. And we can get, again, this kind of qualitative description of these changes. So one of the ideas is to be able to learn these changes using learned models. And then we could incorporate these, and we can fine-tune the understanding of the ECG that we expect from a particular patient, given the torso geometry and the location and the pose of the heart within the torso. We are in parallel developing a similar approach for electromechanics. What I mentioned up to now is just electrophysiology, only electrical activity. Electromechanics is even more computationally demanding. So we have been building a model together with our colleagues at the Barcelona Supercomputing Center and also using PRAISE. So we're building models of electromechanics that incorporate certain things like the effect of the pericardium, for example, on the torsion that the left ventricle experiences during contraction. And up to now, this again, we have followed a similar approach. Again, we can do a limited amount of simulations it is now because of the requirement for computational resources. And these are some of the examples that simulations that we have performed. This is recently published this same year, in which you can see here, this is a slightly complicated plots, but you can see just the difference between the darker dots and the lighter gray dots. These are for values of cardiac parameters that represent a healthy heart. That would be the darker dots and represent disease. And here there are comparisons in a number of these parameters where we simulate clinical metrics such as, for example, ejection fraction. Ejection fraction is just a metric of how much of the volume of the left ventricle, what percentage of the volume of the left ventricle decreases between end diastole and end systole at the end of contraction. And here on the left plots, for example, we can see a clear differentiation in ejection fraction that is given by our model. Again, we cannot do a complete parameter sweep with this because we require a substantial computational infrastructure. So again, there is a role, we believe, for learned models in order to characterize all these interactions. If I move to the next slide. Okay. Sorry about this, it doesn't seem to be working. All right, no, I've gone a little bit. Okay, yes. So what we have been doing in order to characterize this natural variability, in particular from the anatomical side, we have started to look at big databases, such as the ones that have been building up over the last few years. And in particular, I will mention two examples that we have been working on. On the left, you can see the UK Biobank. UK Biobank has up to now scanned cardiac MRIs of almost 50,000 subjects. There's a counter that I just copied here from the number that was there yesterday. It's probably not going to change too much in the next few weeks or months, given the current situation at hospitals. But there's still a few years to reach 100,000, which is the final goal. And many of these subjects are going to be rescanned more than once. So we are going to have, right now, we already have almost 50,000 patients that have been scanned. And also we have a lot of other information about these patients, from health questionnaires to electrocardiograms, blood samples, and so on. These are asymptomatic subjects, so in principle, it's an indicative of the healthy population, and it's extremely valuable for us to characterize what is the natural variability in the absence of pathology. On the right, this is the hypertrophic cardiomyopathy registry, HCMR, and this is a much smaller, since it is a disease-specific data set. It's a smaller one. It's about a little bit less than 3,000 subjects. They have all been enrolled and they are being followed up. And here there will be full outcomes, so that we know we can work towards a better stratification of the disease. We have started to look at these, and for this we have started looking at alternative machine learning approaches. And one of the examples is this work by Leon et al. Here at Oxford, in which the electrocardiograms where this was only 86 hypertrophic cardiomyopathy patients, the electrocardiograms were represented by a Hermite basis. As you can see here at the bottom left, this gives us a collection of coefficients, and these coefficients can be used in a clustering algorithm, and they can be used to see if there are differences in hypertrophic cardiomyopathy. So represented here, one can see that there seem to be a number of separate clusters. And then when we go back to the anatomy as represented in the cardiac magnetic resonance images, each one of these phenotypes can be represented as their average electrocardiogram. Here are the 4 groups, and we see that this is well correlated with 4 different phenotypes in the CMR. So this is just a purely machine learning approach, which then we are linking to the computer simulations by looking at each one of these clusters and the variability between them, and doing these computer simulations with the models that I mentioned before, to see what causes this variability and whether it is related with any of the predictors of outcome of the disease. If we move again to the electromechanics side, we have also been learning electromechanical activities using pure deep learning models. And here we have used CGAN, generative adversarial network. So here we are trying to capture the mechanical contraction of the heart, so the relationship between end diastole and end systole. We are trying to capture it using a purely learned model, an adversarial model in the shape of a neural network, deep neural network. So we have the end diastolic images here on the left, and then we predict using our CGAN, we predict what end systolic should look like. And we can also see what the end systolic images actually look like. We can calculate difference between them. And then we can also segment them using also deep learning models that we have built in-house. We can segment them and look at differences. Instead of looking at differences in the images, we can just look at differences in the shape of the left and the right ventricles here. And then this is the loss function that the system is going to learn. And eventually, then we can do experiments with these. Here there are some examples of what the system predicts. There are 2 patients here, patient A, patient B, left and right. They have the end diastolic ground truth and systolic ground truth. So this is how the heart is actually contracting. And here we have the end systolic prediction. This is what our network has learned that the actual heart should look like, both in the image. This is a purely synthetic image, and also in terms of the segmentation, we can segment both of them, as I was saying before. And here we have the same thing for the other patient. And we have started to look at UK Biobank and also hypertrophic cardiomyopathy patients. We look at UK Biobank, we can see, so we train this, for example, with a population of younger patient, and then we apply this on a population of younger patient and another subpopulation of older patients. And here you see on the top right how the network has become very good at predicting the contraction of the subpopulation that it has learned, and it's much worse at predicting the contraction of the patients from the other subpopulation. Now this has some interest. It's the similar thing for body mass index differences, but not for gender differences. What is even more striking is the changes that happen at hypertrophic cardiomyopathy. So here we can see, this is still at this point, it's a preliminary result. So we can see clearly the differences between healthy contraction and contraction in patients with HCM, and we are hoping to be able to reproduce the things that we've seen in the clustering examples before. Now moving on to my last slide, what we are planning to do moving forward. So what we want is to, first of all, we need to complete the machine learning based pipelines for personalized simulations, going in a fully automated way from the images to simulated ECG or simulated electromechanics. Since we are trying to apply this to many thousands of patients, then we have to have complete, robust pipelines. And this is where we are focusing most of our efforts now and for the next few months. We are looking forward to refine and complement computer simulations with learned models, along the lines of the last presentation, and also analyzing simulation results with machine learning models to generate biomarkers that then are applicable in clinical scenarios. Thank you very much. I'm looking forward to your questions.
So thank you, Vicente. So everybody, please go ahead with questions.
Gerald?
Yes, please.
Peter here.
Yeah.
Well, Vicente, just to ask you about the extent to which in the cardiac area people inside Comp Biomed are doing similar things to you. I have in mind our friends at Barcelona Supercomputing Center. Then they seem to be less active in the machine learning end. Is that the case?
I don't know if there is anybody from Barcelona here. I wouldn't want to talk to say what they are doing. We are working quite very closely with them, particularly on the electromechanics area. So we have been using Alia Francesca. This was before Comp Biomed 2, but within Comp Biomed, Francesca was using Alia for developing in Alia also for the results that we have just published. So that's the idea, is that we are going to continue working with them. And well, some of the things that we need is if we are going to train our models, then we need a massive amount of simulations if we are going to use these deep learning approaches.
I mean, I think the point is, we've discussed this before, and you've made it, is that clearly in some areas, to get results on timescales that are relevant to clinical decision making, you're not going to be running very large scale high performance computing simulations. The closer you get to that sort of sharp end, the more you might be interested in invoking machine learning as a shortcut. So then I'm thinking that there is Mariano Vázquez with his spin out Elem Biotech, who conceivably could be wanting to do that rather than running large ALIA simulations in a commercial cloud. What do you think about that?
I think you're absolutely right. Yeah, that's the kind of line that we are trying to pursue. I think in particular, yeah, even for a single subject. So there are two main lines. One is population studies, in which in order to capture variability, we need to learn this in some way. The other one is even for single subjects, because the number of parameters that need to be fit to the specific subject require a very large number of simulations. To some extent, some of that can be learned. And then, of course, if you want to harness the full power of the computer simulation, then you just do maybe a small number of final simulations using ALIA and supercomputers. But there is no way that this kind of parameter fitting can be done for a specific subject in a time frame that is useful clinically.
Right.
Okay, do we have further questions? Anybody?